Okay, welcome back, everyone. This is the second session for our seed sourcing and end use theme. So we've got 7 talks in this theme focused on germination and establishment, seed longevity and conservation. So the first speaker is actually myself. I'm embarrassed to be introducing myself, but we'll get straight into it and start talking about the work that we're doing in seed restoration in the Pilbara. So my talk is about quantifying seed germination and establishment traits for ecological restoration in the Pilbara region of Western Australia. So the Pilbara is quite a vast, you can see it here, landscape, about 180,000 square kilometres in the northwest of Western Australia. It's predominantly a grassland, terrestrial grassland, and it's quite a pristine landscape actually. That is, except for when we have the mining impact. So it's also a centre of mining activity in Western Australia, particularly iron ore mining. So you can see some of the statistics there, over $100 billion in 2019-20 of iron ore from this region. So the mining disturbance footprint, the published figures are somewhere around 2,500 kilometres, but in fact they're probably at least twice that size. And we are trying to restore landscapes such as this. This is a waste rock dump, so you can see a vast, almost moonscape type landscape. There's a deficit of topsoil due to the type of mining. It's pit mining, so we're really reliant on direct sowing of seed, and the challenges associated with that being that we commonly get very low proportions of seeds establishing. So the research I'm talking about today, this is the concept of demographic filtering. So what we're interested in here is what stages at which seeds fail to establish. So once we've sowed the seed, they need to germinate underground, they need to emerge and then establish. So these different life stages, you can see in some of the published literature down here, there are different probabilities of seeds passing through those life stages. So some of the first work to come out of the US showed that there's actually quite a high chance of seeds germinating, but those that then emerged from the soil, the probability was very low. So this became a key bottleneck. So this was established for 3 grasses. Some more recent research, 47 arid grasses, shows, as you might expect, larger sample size, varying probabilities of success, but that is the concept that we want to test for our species. What are the life stages that are most limiting to seedling establishment? So the research I'll talk about today, we set out to understand how substrate type and water availability influence seedling recruitment, and our aim was to model a probability of seeds transitioning through these 3 life stages of germination, emergence, and early seed survival. And we selected 5 species for this research that are key to successful restoration and representing different plant life forms and seed traits. So I'll take you through in a little bit of detail the experimental design. We used a rainout shelter. You can see this here. We constructed this as at the iron ore mine Mount Wellback, BHP's Mount Wellback mine site, just out of Newman. So within this rainout shelter, we had a number of soil plots. So we had 64 2 by 2 metre plots, which contained different types of soil substrate. So some contained topsoil, and then some contained waste material. You can see 2 types of waste, and then some contained blends, so 50-50 blend of topsoil and waste. So we were interested in, for these species, so we have 2 acacias, an indigofera. These are all from the Fabaceae family, 2 Troideas from the Poaceae. We're interested in how these seeds would germinate and establish in these soil types and under differing watering regimes. So an important part of this rainout shelter was that we could irrigate the plots and simulate different watering regimes. So you can see we applied these 4 watering regimes over a 7-day period, and then we turned the water off and we monitored germination, emergence, early survival and biomass after 6 weeks. So when we did that, this is a photo of the plots after 6 weeks at the time of scoring. So you can see what it looked like there, and these are the main results. So we'll take you through these graphs. What I've done here is grouped the data for acacia and the data for the 2 Torodius species. So both acacias and both Torodius behave similarly. On the left here, we can see the cumulative fate. So this is the proportion of seeds that either germinated, emerged, or established. The data is just normalized for the different species for ease of comparison. We have the 4 different rainfall regimes, and then the graphs are coloured based upon the different soil types. So again, these left-hand panels, these are the proportion of seeds that transition through these different life stages. I think the main thing to note here is, firstly, we have laboratory germination here. So we had some questions about that earlier today. How does laboratory versus field germination differ? So you can see for all 3 species that we get lower germination in the field than in the laboratory. That's not to be unexpected. The other thing that's obvious on this this side of the slide is that at the lower rainfall regime, so 80 millimeters, we get reduced germination. So that's particularly so for the acacias and the indigofera, maybe less so for the Torodius, but it's certainly obvious that there's a reduced germination at 80 millimeters. All of the other 3 rainfall regimes, we had similar germination for the most part. So if we move to the right-hand panel, which is this is modelled data. So this is actually modelling the probability of the seeds transitioning between those 3 life stages: germination, emergence, and establishment. I think what is most obvious here is actually the probability of germinated seeds to emerge is actually very high. So for all species, we found that post-germination emergence was high. So in fact, for this data set, these species, emergence is not the limiting life stage, as in contrast to what was seen for some of the data in the US. In fact, it's germination and or seedling survival is more limiting than emergence. And I think that the other point to note on this graph is the impact of soil type. So seeds sown into the waste types had lower germination, lower survival in some cases, and with Torodius, it's very evident they also had lower emergence. So waste type had a big impact on seed performance, but blending the wastes to some degree was able to improve performance. So to summarise this data here, we've got species dependent limiting life stages, but it doesn't appear to be emergence at this for these species. Rather, it's germination or seedling survival. Plant establishment is likely to be limited if we've got a rainfall of below around 120 millimeters over that 1 week period. And then we can see the highest emergence is happening in topsoil, but if we blend our waste with topsoil, we can somewhat offset those negative effects. So just to finish up, the next steps in this research, what we're trying to do is build a picture of the seed traits that might influence establishment. And really what we're looking for here is if we can identify the limiting traits, then can we modify them through seed enhancement treatments or modifying the soil to improve the chances of establishment. So just one example here I've tried to highlight, for example, for indigofera, this is the water potential at which 50% of the seeds are able to germinate. So this is quite high. These seeds are quite sensitive to water stress compared to the acacias. So that may be a reason why we see lower germination relative to the acacias. So with that, I think I'm about out of time. I don't want to hold up the other speakers. We'll close my talk there. Happy to take some questions afterwards. Thank you very much.
Thanks, Dave. Can everyone see that? Yep. So I'm going to follow up Dave, so I don't actually have to give much of an introduction to the Pilbara, but I'd at least like to acknowledge all the co-authors, one being Dave and the engineering team and our soil scientist, Miriam, and all our partners. So Dave did touch on some of the high impact disturbance that we experience in our mining environment. So in the background here is the typical iron ore pit where the steel products go overseas, but anything that's uneconomical generally gets thrown over the edge and into a waste rock dump, which are these large expanded areas here, made up of a whole range of flat areas and steep slopes. And actually from the top right all the way through to the bottom left is a progressive trial we did last year of about 85 hectares where we staged our research over the summer. And in the middle of that picture is where they hadn't even finished making the mountain yet when we were seeding. And in some cases, there is topsoil availability, but in some scenarios, they don't have topsoil. So these are some of the harsh soil environments and the seeding challenges we have in these arid systems. So for our research, we've got a range of key focal species that we've been focusing on recently. We break down all the quality, cleaning, processing, recruitment bottlenecks. So Dave just touched on seed dormancy, and been working on the front of trying to look at seed enhancement. So once we can get them germinating, how can we further enhance that seed batch? And then we've been working closely with mechanical engineers to look at direct seeding options that might be in the market. Can we modify that existing direct seeding equipment if they don't perform? How can we design and construct whole new bits of machinery? And then working closely with our soil scientists to understand the growing environment, and then also of that soil type, whether we can use the microbes and the beneficial nutrients to add into some of these seed enhancement technologies, such as extruded pelleting and coating, and then a range of field trials. So I'm just going to touch on one pathway that we've chosen for our spinifex or Trodia species over the years. If we just look at one pathway we could choose, is we know that there's a deep dormancy gradient that exists from the dispersed floret unit, and we need to isolate that seed to get some sort of response out of the individual seed batch, and then also further getting more response of that seed batch by using smoke cues. So this was established through my PhD, Wolfgang's PhD, and also Olga Kilodasheva's PhD. One thing we've been doing now is looking at the ability to be able to apply those smoke chemicals through hydropriming. So we've had the engineers build us this scaled seed priming unit, and as well as once we've got those pure seeds and expose them to the priming unit or the chemical, we're then adding an artificial seed coat back onto it, so through the rotary seed coating process. So just in that aspect, we're finding we're getting up to about 40% emergence compared to something like 0% or even 1 or 2% in previous years. But another pathway that we have been taking, if you're not focusing on trying to isolate the individual grain out of the florets, is how can we keep that floret but remove some of the bulky tangling appendages of that material and try to get it to flow better just from a dispersal perspective by keeping it in its actual original diaspore unit. So one invention that we have coming out of the University of Western Australia and the team at Kings Park Science is flash flaming. Effectively just modified with our engineering team the use of a rotary seed coater and custom built these 1 cubic metre flash flaming machines. And so what we're finding with the flash flaming is we can precisely and in a controlled manner remove unwanted appendages and hairs that take away a lot of that bulkiness and the Velcro nature of those hairs and orms and get it much more free flowing. So we're altering that physical makeup, but we're also finding some benefits from potentially weakening of the floret, and so you're getting a physiological benefit of germination increase and emergence potential. So just with all that taken together, where we're looking at the soil component, the seed component, understanding dormancy and enhancements, how else can we actually improve that delivery, also the processing and the delivery of that material to the soil environment? So expanding on from what Dave said with our rainout shutter, we've now taken some of this flash flaming work to the field, as well as cleaning down the pure seeds, exposing seeds to the smoke chemical, and adding artificial polymer seed coats. So coming out of now Dr. Monty Massare's research, he's one of our mechanical engineers that's been looking at some of this work. We've developed a new seeder, which we can't unfortunately go into some of the detail, but we've got a patent pending on this machine at the moment to put seeds into the precise layer of the soil seed bed that we know the seeds have to come out of. And when we first asked the mining industry what's problematic out of agricultural seeding machines, effectively they said they can't seed many native species, they can't get up into the slopes, and they can't sow into rocky environments. So part of the design features of that machine have now looked at that. Also, we know that the further we bury seeds inside these rocky soil profiles, the rocks get in the way, and surface sowing those seeds are also problematic. So we're now targeting about the upper 20 mil of these waste rock dumps, as well as thinking a bit bigger picture. Once we do get some machines that are capable of sowing high diversity mixes for native species, how can we move away from sort of linear agricultural type seeding efforts and getting into something that's a bit more authentic? So with our trial, back to this picture, it was about a 5 hectare site on a flat part of a landform or a waste rock dump. We were lucky in the desert zone to get the rain, which is one of the major barriers that we have. We had Cyclone Blake drop a lot of rain on top of this trial 2 weeks after seeding, so you could almost call it the perfect storm. And then within 4 weeks afterwards, you can see just some of the imagery here from the left-hand side, the rock content we're dealing with in some of these rock environments, all the way through to the right image where we've got some mass emergence events occurring. Pretty picture of all of our seed enhanced material on the left-hand side compared to doing nothing at all and just spreading florets that come out of bags that the commercial suppliers utilise. And within that 9-week period, we started seeing hundreds of seedlings per square metre, comparing it to not many from the untreated material on the right-hand side here. So just crunching some of these numbers, on the left-hand side, we've pretty much got all our florets untreated, commercially applied, status sort of standard seeding practice, where even after the period of 1 month, 10 months or 20 months after seeding, we pretty much less than 5 seedlings per square metre. As you move into managing florets, so the next 2 sort of sets of bars, we've got flame florets and flame florets plus the priming, so in the smoke chemical, and or the next set of bars being seeds managed, which is cleaning them out of the floret down to seeds and then hitting them with the priming or the smoke chemical again. We're getting a 5 to 6-fold increase in initial seedling counts where they're surviving for at least 10 months and all the way through to the 20-month period. So that 20-month period is reflected here again in the green bars. But one thing to note is we've still got up to 5 or 6-fold more seedlings per square metre, but the plant cover now is also averaging some pretty high numbers. So from the take-home message here with a lot of our work is by unpacking that regeneration capacity of our species with our perennial grasses, understanding the dormancy requirements, and then applying a range of seed enhancement treatments. In this trial, we found that the SETs were far better than sort of standard seeding efforts from doing nothing at all. So I'll leave it there and just highlight there with these pictures of what happens when you do nothing or do lots. So thank you for your time.
Lorena sends her apologies, and I'll try to do nowhere near as smart or as good looking as Lorena, so you'll have to bear with me. Lorena and I both work at Biobank Seed, which is a privately run seed bank and research laboratory located in Duval in New England, New South Wales. A lot of the work we do is for large-scale ecological restoration and seed research. So a lot of the places we actually work are in northwestern New South Wales, in the Gunnedah Basin, that sort of area, mainly dealing with mine site rehabilitation. So this talk is on tackling the limitations of seed germination for ecological restoration of Australian native plants in northwestern New South Wales. So dealing with mining companies, about 10 years ago when the focus switched from stems per hectare to also X amount of species per hectare, so the biodiversity offsetting as well as just rehabilitating. The mines would, with the advice of their ecologists, would essentially send us a shopping list of here's what we need to grow on our sites, and they'd usually give us a number of plants or a percentage of each species in the mix, and to them every plant was just as easy to grow as your basic eucalypt, and they expected to pay the same money and have perfect seedlings arrive at the same time as everything else. So there was a steep learning curve going from growing and planting a few easy species to then trying to tackle the full strata, 20 or 30 different species and get them established on site. So Lorena has been studying for a number of years a whole range of species, and in this study she looked at about 40 different common species that all had difficult germinations in this scenario. So there's a fair few issues that can affect the seed germination and make them difficult to use from a restoration point of view. So you have environmental factors. Some seeds acclimatise to a very specific set of scenarios, and are quite difficult to establish at a commercial rate. Seed quality is a problem. Occasionally you are sent seed that someone has collected from a certain area and are expected to grow it, and we all know that if it's bad quality you won't get much of a result. And then a whole range of dormancy issues. So the seed may be viable, but it's got a tricky dormancy breaking scenario in order to get it to go. So out of the more than 40 species, out of the species Arena studied, she found the following viability issues. 27 species were stored incorrectly. 6 species had fungal issues. Something inside the layers of the seed containing fungus that would destroy the germinate once it came out of the seed. Insect predation, herbivory. There's 13 species that contain seeds that were damaged through insect predation, and then 16 species with other issues, and they could include a collection at the wrong time, so that the seed might have been collected too early or too late, even it might have dried out. So you see a lot of these issues just stem from a lack of knowledge in handling seed, and so we we also looked at the germinations for the particular seasons that things came up. So a lot of these were spring germinating, a few in the summer and a couple in the winter, and then here we had a few crossovers as well in these ones down the bottom where they could germinate in multiple seasons. And then from the list of species, we identified that 24 of them had no dormancy issues. 5 had physical dormancy, 7 had physiological, 3 had morphophysiological, and 1 other. So in this slide here, so not only do we have to figure out the triggers to get these difficult seeds to germinate, but we also have the job of pre-treating these seeds if they require it at our own facilities before we use them. So whether it's in seedling production or direct seeding, and this just really highlights. These are some of the seeds that had dormancy issues, and you can see the dark grey part on the graph is the germination percentage with no treatment done to the seed, and then this green bar is the germination percentage of the same seed lot that has undergone some sort of pre-treatment. So if you've got a physical dormancy, scarification of that outer coating is the pre-treatment. So machines like scarifiers, we've got a very homemade version of this in that bottom picture. We're just using a grain mill to try and crush some seed and take it out of that woody outer coat and expose the naked seed before use. So So the aim, our goal here, is essentially to use seed of some of these difficult species and convert that into commercial use. So if the mines want thousands and thousands of plants, and they also want a broad range of species, how do we then convert our techniques so that we can actually deliver? Because at the moment, the seed for these difficult species gets used, it gets sent to the nurseries, or it gets incorporated in direct seeding, but the amount that actually germinate and live is probably very low. So what we're trying to do is identify any issues individual species may have, work out a pre-treatment that's quite simple, and then convert that over to using them in a nursery setting or direct seeding setting, either ground-based or drone. So that's where we're heading with this. Marina would like to acknowledge Steve and Ben Field, who are the directors of Biobank Seed, myself, who's done a very poor job of the presentation, and David Carr. Sorry Lorena couldn't do this, but please send any questions. She might try and attend the question and answer session. Thanks. Okay, so you've got me again. This one's the one that I prepared on seed coating and the effects on seed germination, handling, and the costs associated. So this is also done in conjunction with Lorena at our lab in Duval. So one of the main goals as a business is to improve ecological restoration and sustainable seed use through scientific research and the practical application of that. So we basically want to use less seed of a higher quality to achieve the outcomes. So, what is seed coating? Seed coating is basically a way of enhancing a seed by applying constituents to the surface of the seeds, mainly to change their physical properties and deliver active ingredients. Seed coating is already used widely in agriculture, but we've only just started to explore the applications for native seeds in the ecological restoration sector. Over the last 2 or 3 years, we've been trialling various coating techniques with different seed types to determine whether it's actually viable in terms of ease of use and cost, and whether germination is effective. So how do we coat seed? There are various machines and products used to coat seed that follow the same basic process, which is spinning the seed around in a rotating drum or a pan, and then successive layers of polymers or glues are applied to bind layers of mineral powders to the outside of the seed until you've got the desired covering. So the basic products here are all inert, but you can add active ingredients as well, if you should need to target something specific in the mix. Once the seeds are coated, they're just dried off in a machine to bind the coat, and the coat is designed to break down when it's wet. So if you've got a thick coat, it'll take longer to break down and for the seed to imbibe. Why do we coat native seed, or why are we trying to coat native seed? A wide range of species are used in ecological restoration, and many have physical characteristics that make them very difficult to use practically. They might be small and light, fluffy, spiky, sticky, you name it. So the main reason for coating natives is to create a more uniform product that we can spread with conventional machines. So if it's easier to use, you've got more control over the sowing rate leading to less waste and therefore less seed needed, which is particularly important as native seed is a limited natural resource that needs to be used sustainably. More control of the spreading and added protection of the coat will lead to better outcomes, and using less of an expensive product and minimising failures will reduce the cost. So if we're making revegetation cheaper and more effective, that can only be a good thing. So when we looked at handling, we sort of have two generic examples throughout this talk, and one is coating of native grasses, because that's a fairly wide application. So we wanted to try and spread native grasses using conventional equipment, whether they're agricultural seed spreaders, aerial spreaders, or drones. Native grasses are notoriously difficult to spread because they're often very light and fluffy, or have long horns and tend to clump like some of the other speakers have already talked about. We found that coating individual species or even multiple species grass mixes was an effective way to get around these handling and spreading issues. Even adding a 100% coat, so a doubling of the weight, was enough to flatten all the fine hairs and create a far more versatile product that could be sown with conventional equipment. We also found that coating can enable further cleaning of the sample and remove remaining non-seed material. So handling of eucalypts, this is another issue because direct seeding of eucalypts still occurs, and it's a very wasteful use of an expensive product that's hard to source sustainably in bulk. Most eucalypt seed is so small it's hard to spread evenly or accurately, and so we trialled various techniques to coat eucalypt seed with the aim of increasing the size of each seed or seed pellet in order to control the sowing rate, minimising the amount of seed needed. One technique that worked quite well was to attach the eucalypt seed to a carrier during the coating process. So in this case, we used a grain of rice. During the coating process, this gave us enough volume essentially for the coating process to operate effectively. So if you tried to coat a small handful of eucalypt seed, it simply won't roll evenly in a coating machine, so you have to have a certain bulk of material for any coating to occur properly. So we ended up with a nice uniform product which could be sown with all the conventional means mentioned before. We were aiming at about 3 to 5 viable seeds in each pellet, and you could then control this further by deciding whether to incorporate the seed early in the coating process or towards the end. So if you put the seed in early, it means that it's deeper within the coat. If you put it on at the end, it means that the seeds are actually attached to the outside of the pellet. So if you needed a certain amount of rainfall before your seedlings germinated, you'd embed it a bit deeper in the coating, so it would only break down in the vibe after quite a bit of rain. But if you wanted it to germinate straight away, you could place the seed on the outside of the coat. So you basically have a greater level of control of how your eucalypt seed is spread. This example, I've done a couple of examples of costings. So this one is for a generic native grass. I used Newby Silesium, Queensland Blue, as an example of a normal sort of a fluffy, light native grass. So these costings are based on the hypothesis that 1 kilo of a coated product will perform as well or better than 1 kilo of raw seed. So if we're looking at this example, we've got 1 kilo of bluegrass, which is $300 worth. You spend another $120 to put a 100% coat on it, and that gives you 2 kilos of product. So you spent $420 for 2 kilos, and the idea is that 1 kilo of your coated product will do the same job as 1 kilo of raw seed, even though you have half the number of actual seeds. But the control of dispersal and the added protection of the coat should do the same job. So, then you look at eucalypts, and it's the same thing. It's more expensive. We want to make it a bit bigger, so we increase the bulk 200%, so we're tripling it. It's a bit more expensive to coat, but then you end up with 3 kilos of product. And again, we're assuming that a kilo of the coated product will perform as well as, or better than a kilo of just raw seed tossed out due to that level of control you have. This shows the germination. I'll wrap it up quickly, I'm running out of time. So basically the germination was the same for coated and uncoated, which is what we were looking for. So having a seed coat hasn't limited germination in any way. Sometimes a thicker coat will make it slower to germinate. And the next steps are looking at actual field results. So we've got a couple of trials ongoing now, so we want to see how the performance is out in the field. Then we can take it further by adding active ingredients to our coating and doing any number of things. So thank you for that, and I'll hand over to the next speaker.
In this study, we were interested in looking at how seed attributes and habitat characteristics of Australian rainforest seeds could be related to their longevity. Seed longevity is basically how long a seed remains alive, and within the context of seed banking, this is how long that seed remains viable while in storage. And this information is important to maintain the collection integrity. So seed longevity influences recollection intervals. That is when we go and get more material, fresh material to put into our seed banks, and it can also influence the storage method. So therefore, means by which longevity can be determined or predicted are quite useful for seed bank management. Within Australian rainforest seeds, there is currently limited information on their longevity within storage. Some studies were completed in the 1980s looking at the soil seed bank, and this does provide a bit of an insight that perhaps Australian rainforest seeds are amenable to at least short-term storage. How long do seeds actually remain viable in storage? There's a couple of different ways that we can look at this, and the first is real-time testing. So in this case, we're performing scheduled retesting of collections held in storage. This particular approach is routinely applied in seed banks. However, it has a few drawbacks in that we're constantly reducing the size of the collection. Each time we remove seeds to test them, the repeated removal of collection is exposing it to temperature and moisture changes, which increases aging of the seed. The viability of the collection may have already decreased below the point where you would automatically recollect fresh material by the time you get around to testing it. And you may have to wait years, if not decades, to actually see the viability drop enough to trigger your recollection action. So an alternative to this is to use artificial aging or controlled deterioration assessments. Now in this case, seeds are held in a high stress situation to deliberately age them, with repeated germination tests used to subsequently estimate the relative time it takes viability to decline to 50%. That is the P50 value. But we can also look at characteristics of the seed or the species as a predictor of longevity. For example, this might be seed-based, such as whether or not a seed has a hard seed coat or an endosperm, or they could be habitat-based, including species, for example, which come from dryland environments. So the last three approaches are concerned with prediction of longevity, and the last two approaches are particularly useful because they are really rapid assessments which can be determined perhaps just by looking at the seed or by completing a very simple assay. To assess rainforest seed longevity, we use material from the Australian Plant Bank Seed collection. We selected species which were orthodox, for which large collections were available, having a minimum 84% germination post-storage. 26 species were identified from 18 families, and at the time of testing they had an average age of 5 years old. The species selected included trees, climbers, herbs and shrubs, and they were all collected from rainforest habitats along the east coast of Australia, from the Queensland-New South Wales border, just south of Sydney, from cultivated collections at the Australian Botanic Garden, Mount Annan. To consider the relationship between rainforest seed longevity and seed and habitat characteristics, we first estimated seed viability using artificial aging experiments. From this data, we used a probit analysis to identify P50 values. That is an estimate of the time it takes for the collection viability to fall to 50%. We combine this data with seed characteristics of the various species, plus climatic data gathered from interpolated national climatic grids at the point of collection, so the collection location. We also use the collection site information, such as latitude, longitude, and altitude. All of this information was compiled into an ordinary least squares regression with the P50s as our response value. The model went through a process of minimization until the remaining model, the final model, only contained significant variables. The average P50 value we found across our 26 species was 17.9 days. We had 18 species which had a P50 of 20 days or less, and 10 species that had a P50 of 10 days or less. Plectranthus nitidus had the highest P50 among all of our species at 66.5 days. In terms of our ordinary least squares regression, the model performance was moderate with an R-squared value of 0.5, but it was certainly significant with an F value of 0.02. In terms of the variables that remained in the final model, this included evaporation, maximum mean annual temperature, altitude, diurnal temperature range, and the seed weight. The majority of species we tested were predicted to be shorter lived. Now, this is in contrast to what is usually found for Australian species, which are largely regarded as long lived. We found that longevity increased as evaporation and diurnal temperature range increased, and we found that longevity decreased as maximum temperature and altitude increased. Now, again, this is in direct contrast to what is usually found, whereby seeds that come from a hot and dry environment tend to be longer lived than those which come from cool and wet environments. However, rainforest habitats are somewhere in between, being both warm and wet. So there's some interesting things, I think, going on in rainforest habitats in terms of how their climate are actually influencing seed longevity. We found that as weight of the seed increased, longevity decreased, and perhaps this is a reflection of the surface area to volume ratio of larger seeded species. Now, as they go through the cooling and drying process in preparation for storage, they spend more time at intermediate temperature and moisture conditions, which causes increased cellular degradation, thereby increasing aging of the seed. Now, some caveats around our study include the seed age, being that they were around 5 years old at the time of testing. We only use single collections to represent individual species, and we know that seed characteristics can change between collections and across the geographic range. And the high temperature and high humidity conditions of the artificial aging assessment doesn't reflect the low temperature and low humidity conditions of storage. And so the results from artificial aging don't necessarily correlate with what will actually happen in terms of aging of seeds in storage. So some considerations for rainforest seed longevity. Definitely complete artificial aging assessments and complete them as possible following collection. Use the results of the artificial aging data to inform real-time retesting intervals. For short-lived rainforest seeds, possibly consider cryopreservation if you have the facilities available. Now, obviously this is more amenable for smaller seeded species, but as alternatives, perhaps consider the storage of embryos or other tissue types. And if none of these are available or suitable, we can always fall back to living collections for the long-term conservation of rainforest species. Thank you for listening.
Hi, my name is Dr Duval and I work for the ASSC Conservation Centre. I'm going to talk briefly about one of our major projects which focuses on nationally threatened orchids. We're a partner in the Back from the Brink project being delivered by the Hills and Florio Landscape Board. We work closely with the project leader, threatened flora ecologist Jerry Smith. It's a 5-year project which aims to deliver on the recovery of 19 nationally threatened plant species, and this includes 13 nationally threatened orchid species. The ex situ conservation tasks for the ASSC Conservation Centre in this project are to survey for new populations, monitor some of these orchid populations, undertake long-term storage of seed collections and fungal isolates, undertake symbiotic in vitro propagation, and to deliver translocations for some of these endangered orchids. This work has been augmented by many in situ actions such as ecological burning and slashing, weed management, constructions of exclosures. These threatened species occur on many different types of land tenure with many different partners from landholders, volunteers, students, researchers, ecologists, rangers and so forth. One of the case examples for this project is Murphy's leek orchid, Prassophyllum murphettii. This is one of South Australia's most endangered orchids and is endemic to the fluoro swamps south of Adelaide. 4 years ago, it was known reliably from 1 to 2 flowering plants at a single location. As of last year, 2020, we'd found up to 700 plants in total across 7 populations, and these included new populations. We've also since banked 7 million seeds from 4 populations, and hundreds of plants are being propagated for translocation at the Royal Botanic Gardens Victoria by Mark Freestone and Nushka Reiter. With some site managed at a couple of new sites in 2020, along with some favourable seasonal conditions, we're anticipating our plant counts will be in excess of 1,000 plants in 2021. We'd like to share the success of this project to date with some of our landholders and other partners. So we're having an Orchid Conservation Open Day. We're inviting our volunteers, students, researchers, staff at the Department of Environment and Water, and many people that have been involved. And this Open Day is going to be on the 27th of August. But we'd like to thank many partners that have helped the success of this project to date. Thank you.
Hello folks, I'm Jan Vos, the creator of the Botanical Gardens Chateau Pérouse. They started 17 years ago. We specialize in Mediterranean and adjacent biotopes from all over the world. Today we do this with a team of 7 botanists and 7 gardeners. The garden has now a size of 35 acres and will be expanding to 180 acres. We are in a small part of the French National Collection of acacias. Most of these species are planted in the test garden. For now we only have nurseries and test gardens. In these gardens we are creating biotopes, soil types and stable microclimates. So in the future we will keep 25 acres of these test gardens and nurseries to sustain our research work. The garden is now home to 8,000 plant species and 4 French plant collections. In total we are working on 20,000 plant species, and here I show you a part of the French National Collection of eucalypts. As you see, most of our bigger eucalypts are cultivated in 800-litre air pots. We are sowing at least 3,500 plant species each year. All the information can be found in our online database, including sowing protocols and results. Of course, this can be improved and suggestions are always welcome. We are sowing mostly in shade houses like you see here, but we have also different other techniques. and we try to be as close to nature as possible and to ensure the best possible acclimatization. Sourcing of good seed material from known localities is a problem, as well as phytosanitary regulations.
Just move to questions now for the speakers. If we've got everyone on board, looks like it. So we've got a few questions. So Georgia Curry, I don't know, throw Todd in the deep end with this, I'll try and answer it myself. Georgia has a question regarding mine site rehab and what can be done to rehabilitate tailings dams from gold mines in WA where toxic chemicals are present. So yeah, I guess we're really in the realm here of the even soil science to try to ameliorate some of these toxic issues, accelerate soil reformation. I mean, I know people are looking at cover crops, everything from even lupins, I think, as nitrogen fixes to try to get nitrogen cycling going and mobilise phosphorus in the soils through to Marianas, salt tolerant or species that are tolerant to alkaline soil conditions, these kinds of things. I think surface cover design, so looking at incorporating rocks into the soil surface to improve microsites, these kinds of things. But equally, at least from my perspective, it'd be fair to say that some of these areas are fairly challenging to deal with, and unless you can in some way ameliorate those toxicity issues, you're going to struggle to get any plants to grow, let alone what may be something approaching, the vegetation community as their pre-disturbance. Todd, if you got any other thoughts there? It's not an area we've been particularly active in recent times, but
yeah, no, we'll just quickly, in a nutshell, we generally in our mine rehab programs that Dave and I both touched on, we deal with non-hostile side of the mining landscape and those tailings dams and other more hostile like acid rock drainage in a bit more of the bioremediation space. But there are soil scientists really working that space through microbial recreation of the soil formation. Long Bin Huang over at University of Queensland will be one of the leaders there. We are lucky where we don't typically deal with those hostile sides of the landscape, but one area we are touching on at the moment with some of the soil team is those veg cover systems. Can you cap it with something that's a bit more favourable and then create a community above that so you don't actually interact with the underground nasties?
Yeah, thanks, Todd. There's a related question from Bryn to myself, just asking about when we saw reduced germination establishment in our waste types, whether it's the lack of nutrients or water or the dumps toxic. So as Todd talked about, the sites we're working on, waste dumps are not toxic per se. They're certainly a little depauperate in nutrients, soil carbon, microbial activity, those kinds of things. But those factors are certainly important, but probably more so when it comes to longer term plant establishment and growth. I think possibly what we're looking at in the early establishment phases is just about water availability. So we know the waste types, the plant available water is less so than the topsoil. So I feel that that's probably what we're looking at in this case. So sorry, I'm just looking across multiple platforms here, but we have another question then from Stephen Bruce. This he asks, is there a commercial business that will coat seed for clients on the East Coast? So I'm not sure of one myself. I don't know if anyone over the East knows there's anyone active over there doing that service, perhaps. Yep.
Mute myself. We're just getting into it, but it's the sort of thing that could potentially pop up almost immediately if there was a demand for it. We've got a fairly low-level coating machine, so that's probably our only hold-up. If we had better machines and could handle more product, then if you want it, we can do it.
Very good. Okay, question for Zoe from ASA. Really interesting study. A lot more studies needed for seeds from rainforest species. So she would like to know if you consider looking at microclimates from the site of collection. So in some forests from Indonesia and Malaysia, temperature variability can vary substantially, particularly for the riparian understory areas, but with humidity still high. So I think your question is just, yeah, have you looked at microclimates from the site of collection and whether that may have influenced the behaviour you're observing?
The short answer is no, but I definitely agree that yes, it would be worthwhile. I think we've only just kind of really started to look at longevity of specifically rainforest seeds, and then the next step that we've taken is then directly comparing that to seeds from other habitats within Australia. But then I guess there's any different number of ways that you could go from that point. So yeah, it's definitely worth looking at.
Thank you. We have a question from Lydia. This is for everyone, if it's allowed. I'm sure it's allowed. It seems like every species needs some special treatment to improve restoration outcomes. Some of these are widespread. Any ideas how we can share what is learnt in each restoration site to help speed up the initial planning steps of what to do for each target species? I can throw that to the floor for a moment. Or
It's a classic question that all of us
Yep.
attempt to try to find that golden rule. And Lydia would know well and truly from some of our time here in WA that that's not a simple prescription for many of our species. But I suppose we've been trying to get to that because we quite often get the mining companies ask us, you know, what's that? What do we generally have to do? So we've been trying to come up with a bit of a decision tree. Probably the biggest bang for your buck, I reckon, happens is anything that's dispersed in a florid or a papery crack. I think going straight down to the pure seed layer always gives you immediate big bang for your buck. But that also then needs those protectants of the seed coating and other techs that we've been looking into. So I think that in that physiological dormancy, grass, amaranthacea, Tylotus space of a lot of the desert plants would be a quick win. Acacias are pretty routine. And then the other talk about obviously seed coating with ukes and try to increase their seed size and distribution would be another big bang for your buck. But that's, yeah, it's very hard to do general rules.
Yeah, I mean, I think maybe, you know, you can think about plant functional types or life forms or dormancy types and approach some generalisations there. But, you know, we've certainly got species-specific, site-specific issues. And I guess perhaps part of it is also just trying to get better uptake of what we already know helps the, you know, the processes. So communicating those messages. So, yeah, we can dive deep into what are all these limiting factors, but there's many things I think we already know about that can improve processes. So whether that's you know, just handling and storing seeds correctly, you know, we know sowing on the surface, for example, is generally not good. Sowing too early, you know, well before the wet season, we know is usually not good. So I think that's part of it. And then also just what I tried to allude to in my talk was really identifying what are the major limiting steps. So in our case, it appears if it's germination limiting step, well, then we need to focus predominantly on dormancy. And perhaps it's not necessarily about fully optimizing every part of, you know, this chain of seed use, as we like to say, but just where are the major wins just to you know, get the systems looking a lot better sooner rather than later. So sorry, as I was speaking, there's a question for Albertus, and I think we'll come back to when we can try your talk again. But Kathy offered us if your germination database is available online for people to look at.
Yes, it's entirely online. And you have the database which is helping you to select records. And you have a link button for each taxa. and there are 20,000 species.
Okay, very good. Question for Todd from Bryn. How much extra time or resources are needed for seed enhancement? Is there one tech that stands out as the most beneficial, do you think?
That's not a simple one either. Yeah, the cost always comes up as well. It was touched on in the other coding talk. Currently, our commercial costs for flash flaming a kilo of seeds about $70 per kilo. And part of the comparison there with some of the other coding examples is with the data set we have, if we increase seeding establishment by 5 or 6-fold over 20 months or 2 years, that $70 you spend per kilo is far outweighs the original cost. So I would say flash flaming is commercially available at the moment for some of that stuff. And coating, we've never crunched the numbers for our polymer coating process and or the extruded pelleting, but I'd say it'd be either around that $70 mark, $70 per kilo, and maybe less. So I think if you can prove the biological response is far better by doing the enhancement, which I think is true once we get it right, it's going to far outweigh doing nothing at all. And that was evident in our recent trial with that effort.
Yeah, thanks, Todd. Okay, so I think that's all the questions for the presenters we have online. So we can go ahead and close our seed sourcing and end use session. Thanks very much to all the presenters for today. It's been a really enjoyable day, and apologies to everyone watching just for a handful of technical glitches, but I'm sure that you still enjoyed the day. And I'm going to now throw to Damian Wrigley, who's going to close the day out for us. Thanks very much, Damian.
Thanks, Dave, and thanks everyone in that team for your insights and for sharing so much of your knowledge with us. It's been fantastic. I'd just like to thank our sponsors and our partners once again for your contributions to making this conference what it is this week. We couldn't do it without you. We really, really appreciate it. I also just wanted to touch on a couple of housekeeping issues. Obviously, apologies for some of the technical issues. If you are having troubles, please feel free to email RNX and ask them to help you out. Otherwise, there are some troubleshooting links on the conference portal. If you're going to do any social media, please feel free to use hashtag #SeedScience2021 and tag Seed Partnership when you do. Tonight we have our social networking event on GatherTown. It's a fully virtual platform that allows you to create your own little avatar, have a bit of fun, and actually walk up to each other and have a chat. There's also some great resources and a bit of fun for you in the early and middle career research and networking event that Dr. Suze Everingham is hosting at 6 p.m. And for the rest of you who aren't joining in that networking event, just please feel free to join us on the platform and have some fun. Bring a drink, have something to eat, everything's allowed. We do ask you to be respectful and courteous. And if you have any troubles getting in, the password is Germination with a capital G. The link is in the banner above the main conference platform sessions. Tomorrow's themes, we have Seed and Gene Bank Management and Seeds and Culture and Society with Dr. Sal Norton and Dr. Eleanor Brennan, as well as Dr. Terry Jenke, Professor Brad Sherman and Dr. Ola Westingen. And of course, tomorrow morning, we have the launch of the germplasm guidelines. So I encourage you all to come along at 9 a.m. for that launch. Thanks very much, everyone. Hope you've enjoyed today. It's been great fun bringing this to you. We look forward to seeing you tonight and again tomorrow. Thank you.